So my name is Frédéric and Minh, and I'm teaching math at the EuroProofNet Engineering School. It's in Valence, near Grenoble, and it's now since 11 years. And also I started a PhD 2 years ago. So in this talk, I'm going to describe a new environment. I'm teaching a proof in high school named Yalep. So before I space, I tell just a word about the origins of the problem. So, like many teachers, perhaps you, I experienced the fact that at various levels of education, learning proof is hard for students. Why not trying put proof assistance in students' hands to help them experiment with proof? It's like a practical approach to proof. They would have feedback, instant feedback, frequent feedback, and this would help students to consider proof as an object that can be mechanically verified. So from those from all those arose the idea of making a PhD to have the opportunity to explore some interesting questions related to this educational setting. All right, so in a survey that we published with my supervisors, we showed that there really are many experiments. The idea of teaching with proof assistance is as old as proof assistants themselves. And they have been conducting that at various level of education. Among all these things, Julien Arnaud taught with proof assistance in Strasbourg, and I personally taught a few years with math courses with proof assistance in Valence with first-year university students. And also there is a sort of enthusiasm for this subject at the moment. For example, we are a member of a research group called APAM in France that mixes didacticians, mathematicians, and computer science around this subject. The tools also used for these things are very diverse too. There are people that are teaching with dedicated, with general purpose proof assistants like Lynn, like Koch, like Isabel, and people that develop dedicated proof assistants also, and people that adapted general proof assistants to the educational setting. So there is a analysis by Meyer and Barcia that help classifying all these tools regarding their possible impact on learning. And among all that, some tools are based on a graphical user interface, so that the student activity mainly relies on pointing and clicking. So since the peacock of Yves Berthaud, there have been many tools like that, like Eduquera by Rodi and Duhamel, like deadduction, which is based on Lean 3 by Frédéric Leroux. And even though they seem quite easy to start with, as the a priori analysis that I was talking about points out that they could invite the user to click around and make by trial and error, preventing from understanding the very structure of proofs. So as opposite, leaving students the initiative to construct their own proof could give them opportunity to make mistakes. And so that's why we decided to focus on systems that expect textual input, which raises the questions of the input language that we accept. Another thing, most proof assistance software for education are rather geared toward the university than the high school expectations. And there was an know the called TPE, Theorem Prover for the LG Gifted Use Educational Project by Sommer and Nichols, that was pretty convincing and designed towards high school, but not only it takes the years 2000, but also it is a point-and-click system exclusively. And that's why we chose to focus on designing an appropriate language for high school students. So writing something for high school for proof could appear like some sort of a challenge. It's something that would be accessible to high school students, would be a fortiori accessible to undergraduate students, for example. And this is also an interesting period of learning. These are the first experience students except some gradually disappearing geometry from the curriculums. And what is specific to high school proof? It is still rather informal, rather short proof compared to the very formal proof assistance. And the quantifiers and the logical connectors appear, but in plain text only, not with symbols. What is specific to the high school context? You have students that have no background with proof assistance, no background with computer science, and there are very little background with proof. The teachers have no supposed background in computer science or in proof assistance, and they often, usually, have quite little background in logics. And in the high school context, there is no opportunity to have additional training tutoring sessions to learn proof assistant, to learn a tool, to learn a syntax, etc. And just one, because we have some experiences with French high school students. So what is specific to the French high school curriculum, it recommends to primarily guide students toward the truth through proof. And these are the translated word of the official curriculum. And it preconizes some example proofs. For example, the fact that the square root of 2 is not rational. And it recommends an initiation to logical connectors and quantifiers, but very gradually and without the symbols, as I said before. So as okay, so I show just an example. This is, for example, an exercise to prove that n times n plus 1 is even. So that could be what a student would write. I'm cheating a little bit here because it's not a genuine student copy. I didn't have that under the hood for this particular example, so I found that on YouTube, sorry. But this could be, so what you have is that it's very informal. And this could be what a teacher expects. So this is not from the internet, this is from a paper of Fabienne Venant, which is a didactician. And this is the proof in proof assistant lean without any adaptation. So you can be sure that there is some sort of a gap between the two. So as a guideline, think about that. We designed a pedagogical progression on the theme of parity of integral numbers. And this progression leads to the proof of irrationality of the square root of 2, which is in the 10th grade curriculum. And the irrationality of the square root of 2, although it's somewhat emblematic in the proof assistant community, since Vidi used it as an example in his book to compare 17 proof assistants. So this progression satisfies double constraints. The first is to explore the introduction and elimination of all connectors, all logical connectors. And the second is to have an internal consistency in the sense that by it is gradually establishing all necessary results to finally prove that this parameter is irrational. So these example proofs enabled us to imagine the proofs that students could be expected to produce. And this process is at the basis of the design of Yalep, which is the name of the software, which means yet another learning environment for proof. And the very first version of Yalep was only an ad hoc tool to implement this pedagogical progression. So we conducted two experimentation in December 24. There was we animated a 2-hour workshop with 9th graders on the first items of the process progression. And it was only with lean, the bare lean, with some quick and dirty tactics to evaluate our needs. And in June 25, we had a 6-hour workshop where we tested Yalep, so this software, with 10th graders, and some of them did the whole progression. And personally, I'm about to test Yalep with my first-year students this year. So now I think it's time to give you a taste of what the Yalep proof looks like. So a typical proof starts with a header specifying the context and the goal, and ends with a white square delimiter. Basically, a proof in Yalep is only an ordered list of facts, which makes Yalep a declarative language, and each fact may be deduced from the previous ones. Neither facts nor assumptions need to be labeled. Facts can be either justified by the subproof, either be left unjustified, provided that the system can automate and find the proof, or either justified by a short. Some syntactic sugar enables students to avoid symbols that may be out of their curriculum, like quantifiers, like logical symbols, or number sets. And there is also some specific syntactic sugar for the statements, enabling, for example, to avoid functional notation for predicates, so that n is odd is allowed to place odd n. And the remaining vocabulary is small. There are very few other tactics than stating facts. Namely, there are only three: introducing the for all connector by let, assuming assume, introduce the implication, and update, which is does not appear here, but update for eliminating the existential connector. Usually, as I said, there are a few opportunities to offer students specific training on proof assistance, and we have features too that are usually not familiar with this kind of software. And so, how should we define the language? The idea is that we want a language both readable and writable by students without specific training, and that allows to clarify the structures for students. To be easily readable, it has to somewhat imitate some usual pen and paper formulations. To be easily writable, it should have a minimal vocabulary, except the vocabulary for statements. Students when working with proof assistants, they often say, I'm failing because of the syntax, but in math, I would have been able to prove it. So we want to reduce that type of bias. And to enhance clarity, the vocabulary, non-ambiguous, not in the sense of ambiguous grammars, but in the sense that a same word should correspond to only one proof constraint or proof concept. So first, I would like to stress that we do not want to parse natural language like in an approach. We saw a talk about an approach, and this is not in our objectives. Here you have a proof that is written in DProch, which is a natural language developed by Berlin for educational purposes. And you can see that, for example, the word let is used for 3 different constructs to introduce for all, to introduce the implication, and to eliminate the extension. And as, for example, Philippe de Bot and Santiago Amilete showed in their talk the other day, there are a lot of ambiguities in implicits in math discourse, and rather than writing a parser that copes with this, we chose to impose a rigid, minimalist, and explicit language that forces students to clear up ambiguities themselves and to build tight associations between words and grammatical constructions and proof concepts. So our objectives are really different from, for example, an approach with Adrien Delon and Peter Koepke, and approach. I mean, we do not intend to parse the proofs. Now, I will review different proof assistant dialects. Note that all the scripts that I will display are flavors of the same proof assistant language, namely Minh. I mean, these are only styles of writing the same proof assistants. At the beginning, were proof terms. They have the merit to naturally exhibit the proof structure and transport the idea that the proof is a mathematical object beyond the bare process. But manipulating them requires some training in functional programming and, for example, for verification. So proof terms can alternatively be built by sequences of tactics, which results in a procedural proof script. Such a procedural proof script is not meant to be read directly, but instead to be interactively replayed in a proof assistance using the proof state display. So the interactive proof assistant displays the proof state at any point of the proof. So in a declarative style here, no, it's not. Sorry. Okay. So this is still in Minh, but this is most of a declarative style, and the emphasis is placed on facts, statements, on stating intermediary facts, down to granularity, allowing short communication. And declarative scripts are usually meant to be readable. So, as I said, the 3 excerpts of the same proof are all 3 in Minh, and I knew that. Sorry, if I knew better Isabel Isar language, I could have given the declarative version in Isabel Isar, which is a famous declarative language. But here you can see that different styles can be freely mixed in the same proof assistance. So it is not a clear cut, the limit between procedural and declarative. Rather, we say that there is a sort of continuum from procedural to declarative. So these are controlled natural languages for education, and they could contain a mix of declarative and procedural. They are characterized by a syntactic sugar that redefines original tactics and renames them better fit the vernacular language, and possibly to change the granularity of tactics, of process. And the goal of this is only to improve the skills of writing a proof in a proof assistance, transfer them into skills in a pen and paper proof. And the fact that the languages are restricted induces a bias. It makes user believe that they can write anything they write on paper, but actually they can't. So a remedy is to make gradual extensions of the language variants, try gradually to embrace more and more idioms. As far as I know, there is no policy to know what you add to these languages. Okay, so among these, how do we select what we need? So from procedural scripts, we want to keep the display of the proof state because it's the first step of interactivity. But we don't want to keep the fact that this proof state display is necessary to understand the proof. From declarative proof script, we want to keep the fact that it's based on the list of statements, but we don't want to keep the fact that there are proofs, the justification at each step is necessary. And from the natural control languages, we want to keep the syntactic sugar thing, but not the fact that the vocabulary is extensible and gives the illusion to be natural. Now, the question is how to achieve this objective of minimality without, if possible, reducing the expressivity. First, reduce the redundancy of keywords. For example, introduce the for connector, let it alone, but not fix, not take, or whatever. Then, disallow all imperative comments. No unfold, no rewrite. The user can state new facts for doing these actions. He or she does not need specific comments. And then allow unjustified facts, not really unjustified, but the system tries to verify them in the background. For example, for the equivalence, instead of writing, we have P equivalent to Q by combining the fact that I know that E implies Q and Q implies P, just write, we have P is equivalent to Q, which saves this combination vocabulary. And also automatically destruct conjunction each time they enter in the context. For example, if you have a new assumption P and Q, then automatically enter in the context a proof of P and Q without saying anything. And finally, the forward chaining style helps reducing the vocabulary. So just a word about that. The backward chaining consists in taking proof actions that modify the goal or create new goals. So, for example, in the right-hand side here, this is a quasi-lean verbose script. The tactic we discuss here automatically opens two goals. First goal is n is even implies n plus 1 is even, and the second goal is n is odd implies n plus 1 is even. So the order of processing, the goals are open automatically. The order to process them is imposed by the system, and making a case disjunct here requires a specific vocabulary, which is we discuss. On the other hand, so the script on the left-hand side is Yalep. Forward chaining consists in working from assumption and particularly deducing new assumption from previous ones. So the same case disjunct can be achieved by the user explicitly stating that n is even implies n plus 1 is even, and stating that n is odd implies n plus 1 is even. So the conclusion then n plus 1 is even at the end is accepted without justification, which saves some vocabulary. In math education, the written trace often favors forward chaining, but the oral explanation or the draft construction of the proof would involve backward chaining. That's why we will propose to recover this backward draft feature with the graphical interaction. So we'll see that later. Just a quick word to justify that we chose Lean to do that. Probably it could have been achieved with the Coq ecosystem or with the Isabelle ecosystem, although I don't know enough this to be sure. But we wanted first to rely on the system because we want to have this interactive state display. And among the Lean features, there were some things interesting. The parser is very flexible, configurable, which is very convenient to make syntactic sugar, etc. The library, parse library, is very comprehensive. It's supported by a community, and this will make it easier to expand Yalep to new topics. And there is a powerful information, and there is also some interaction with GUI widgets in JavaScript. So we want to program some interface, it is available. And finally, there is a web interface that we tweak for our purposes. Okay, so in the two following sections, I'll say a word about the difficulty that is generated by the type theoretical foundation of Lean proof assistance. First, considering the numbers, and secondly, the partial functions, and how we coped with this in Yalep. So, okay, so this is Lean bare code. Okay, this is not Yalep. This is only Lean, and this is a proof that the square root of 2 is error. I will zoom in a minute. Okay, so Lean and ROG have type theory as foundation. So each object comes with its type judgment. This sensibly differs from usual math practice based on set theory, where theoretically objects are sets. All objects are sets, but predicates determine their kinds, like X belongs to the rational, etc. Sometimes we can avoid mentioning this foundation to students, but it can become inconvenient when, for example, several number types are to be manipulated in the same proof. As an example, there is this proof that the square root of 2 is irrational. This is part of our progression, and this is also part of the French high school curriculum. So before zooming, just note that how here is defined the set of rationals, like the set of reals that can be written P over Q, with P and Q integers, and P, and it is false to say that P is even and Q is even at the same time. And so the last part is just to avoid too much number to read this example. So it's not what I want to focus to, but rather you see that when writing that X is P over Q, the integrals P and Q has to be coerced into reals. And sometimes this coercion can be automatic in Lean, but sometimes it does it wrong. So I zoom on the first part. So in this part, we deduce that P squared equals 2Q squared from the fact that the square root of 2 equals P over Q. And in this section, F6, the P and Q are systematically coerced to reals. Note that it would not work if we didn't coerce, because here it is considered as an integer in the second line, whereas in the third line it is a real that is expected. And then in F7 there is a Lean specific tactic using the activity of coercion morphism that takes it back to the integers. So to solve this, Berthaud and Porté advocate for a unique number type. They propose a formalization of the natural numbers as an inductive predicate over the type real. In Yalep, we keep the same idea that all numbers are of the same type. We name that type, we name it number. Currently it's implemented as real, but in the future it will be implemented as complex. And any subset is represented as a predicate over a number. We only expose the user a set that is defined as the image of the subtypes under the coercion morphism. This definition remains private. The user only sees the set. So this same mechanism generalizes to natural numbers, integral numbers, or rational numbers as well, without different development. What we lose, the fact that with number types, the stability of number types under operations are free because it's judgmental, it's definitional. Whereas here we have to prove because it becomes propositional, and this proof must be automated. It should not be visible by people. So, like suggested by Berthaud and Porté, Yalep has a mechanism of type class inference to trigger this automation seamlessly. And also, we lose the computability over integers. So Berthaud and Porté restore this computability, but for our purposes, we don't need computability. We totally assume the non-computability of this. So here is now the same proof that the square root of 2 is irrational, written in Yalep, so that you can observe that number types do not appear anymore. For example, in the quasi last step, it uses this named theorem proved just before in the progression that says that if the Q squared is even, then Q is even, and this theorem requires that Q is an integer. But here in the context, you only have that Q is a natural number. So here you have the type class inference to deduce that Q is an integer by being a natural number. So in the following section, I will show how we represent partial functions in Yalep. So we say partial function when thinking at type function, but for students and mathematicians, they are total function over sets. So proof assistance based on type theory manipulate type total function like f from a type alpha to a type beta. And this is a very old problem with type partial functions. In a paper of Bidisch, he cites De Bruyne to say how it is old. In the educational context, we expect that the internal representation of a function encodes domain and codomain of the function, and that the application of a function to an element generates a proof obligation that the arguments belong to the domain. Okay, so encoding an object with its membership to a set is possible using the subtype associated to the set. So here we denote by upper row D the subtype associated to the set D. That is the type of dependent pairs constituted by an object of the reference type is here alpha, and a proof that it belongs to the set. This solution was discarded by Sacerdotti, Cohen, and Zolli in educational context, since asking a student to consider a proof as an argument of a function is totally out of scope. And to fill this gap, we propose to hide the mechanism into suitable syntactic sugar and automation. So we intervene at two places. First, when applying a function here, f of 3, an automatic, so normally it will be f applied to a pair of 3 and a proof that 3 is in the domain. And here we hide an automatic proof of this into the notation. And this enables to restore the notation f parenthesis x that is more usual in math than f space x. So two things at the same time. And it intervenes also when defining a new function. So when defining a new function, we have to justify that the image of any element of the domain belongs to the codomain. And again, we hide the silent proof into an appropriate syntactic construction. So that these two things not only are syntactic construct, but also hide some automation. So this representation is okay, but has some problems. First, a function is typed as a function with subtype, and this exposes its types. And we want to hide types. And the second drawback is that the homogeneous equality between two functions with judgmentally distinct domains and codomains will not type check. Even if you proportionally have the same domain and codomain, then you cannot write that two functions are equal. And this can lead to weird considerations. How to define, for example, the set of derivable functions that equal the derivative, since the fact that the domain of f prime equals the domain of f is propositional. So to tackle this, we propose to encode a function with a structure, and in the structure is encoded the domain, the codomain, and a type total function. So doing this, we lost the proof obligation that we had in the previous representation. And to restore these proof obligations, we are committed to the discipline of always manipulating such a structure through the first representation. Back and forth between the representation being allowed by a canonical bisection. For example, when you want to apply a function defined in the second representation to an element x, first you convert it into the first representation, and then you apply the first representation function like in the previous slide. And on the other side, when you want to define a new function in the second representation, you first define it in the first representation, and then you convert it in this structure. So now, no, the time. Okay. So now I say a word about automation. In this project, the automation is essential to fill the proof gaps and to ensure that a reasonable proof granularity is between the proof steps. And we will show two examples how the automation comes into play. So again, I show the first proof. You have this fact that n is even or n is odd, and it is allowed because the system silently manages to find a relevant assumption. Here is the only assumption for all integer n is even or n is odd, and eliminate automatically the foreign connector in it. When writing byproduct even, the user specifies the lemma type. It is explicitly specified because this named lemma has been written by the student just before. So it is in the progression just before. And the user specifies the lemma, but he or she does not specify the objects and the assumptions to apply it. So choosing them is up to Yalep. The second call to predict event here would result in the fact that n+1 times n is even instead of n times n+1 is even. So the automation comes to rescue to unify modulo commutativity. And the conclusion is obtained by elimination of the R connector by detecting that all the pieces are of a case disjunct are in the context. Now, let's take another example, the irrationality of the square root of 2. So first, the elimination of the existential quantifier brings into the context a statement in conjunctive form. You have here the statement Q is non-zero and square root of 2 is P over 2 and P is even and Q is even is false. And each time a new conjunction of the form P and Q fits the context, it is automatically broken into its terms P and Q. So here you have three facts entering the context. The computation hides the variety of tactics, rewriting, applying literal manipulation in rings, or fields, or numerical computation, etc. To state that P squared is even, the system has to introduce automatically existential quantifier. The lemma asserting that Q squared is even implies Q needs that Q is integer as a premise, where the context contains Q is natural, but we saw that just before. So the class inference enables to fill the gap. And finally, the last contradiction step has to figure out that P is even and Q is even as a unique statement, which results from the silent introduction of the connector and, because the fact that we know is on the one hand that P is even and on the other hand that Q is even. A last example about automation. How does it come into play when manipulating type partial function as described previously? To define a function, a proof must be found that is well defined. To apply function, a proof must be found that arguments are in the domain. Note that here the required assumption, for example, to prove that y is in the domain, you have to prove that y is greater or equal than 2. And the assumptions are in the same statement. So to have this assumption available proof, which is hidden in the parentheses here, information, we have to redefine the statement P and Q. Because in P and Q, in the context of Q, you do not have. We need a contextual M, which is defined as for all proof of P, we have Q instead of barely P and Q. And we have the same thing for implication for it. So, as we said, Yalep is based on forward chaining, but backward chaining is used in oral explanations or in draft construction of proofs, and we have possibility of graphical interface that restores the possibility of backward chaining. It could appear either to introduce a connector by selecting the goal, or like here, to eliminate a connector by selecting an assumption. You select, for example, the assumption, a button appears, propose the elimination of the connector, and some Yalep forward style code is automatically inserted with gaps that are denoted with the question mark here. I'm going to, I don't know what time is it. Just to note quickly the demo. I think almost 1 hour. Okay. Okay. So to conclude, Yalep is geared toward high school students, and it features. So it features a minimal interactive language based on forward chaining. It features enough automation to allow most basic steps to be left unjustified, and a mechanism to hide type foundation of the underlying proof assistance, namely a transparent handling of user number sets and a transparent manipulation of type partial function. There is so the Git is public, and there is also a web interface public also to try it. For us, Yalep is really working best. There are many things still to do in it. For example, we have to work on the automation because it's too slow, and there are redundancy. It has been optimized at all for the moment because we were concentrated on the features, and we have to work on the feedback that is rendered by the machine and the pretty printer. For the moment, it's not really understandable by students, and we want to extend topics and the subjects that that are possible. So I don't know if I have the time to show a quick demo or not.
There is one interesting. I think it will be very nice to see.
Okay, if you wish. But the problem is that, yes, with Zoom, okay, I can share with Zoom, okay. Okay, so Zoom and share. So I quickly show the website, which is only a tweak of the existing web interface, but I do the rest of the demo in Visual Studio Code because I don't trust the stability, and also it's not the last version. So okay, this is that's share. See, perhaps we can zoom.
I don't know in the auditorium, but here it's very well designed.
Okay, I zoom. Nice. So this is web interface. So you have only to import the library, and you have here the header, and have here the display on the right. Okay. So nothing else, and the widgets are also available here, but perhaps it's a bit I don't really fluid. I can try another proof, for example. Let's take this. So we assume that n is integer and is odd, and we prove that n plus 3 is even. So the first fact that there exists an integer k such that n equals to k plus 1. So this appears in the assumptions. Then we have an imperative command, which is obtain. So if it exists, let's obtain the k. And then we can compute. So n plus 3 equals 2k plus 1 plus 3. And that's why it equals 2k plus 2. And we could probably conclude that there exists an integer j such that n plus 3 equals 2 times j. And this is what we wanted, that n plus 3 is even. So the proof is complete, but as you can see, it's slow, but it's terminated. It's okay now. In the right, have no balls, so it's terminated. Okay, and you have this also in Visual Studio. I don't know. Oh, yes, I wanted to show.
Does this interface have the example that allow you to do what you showed, where it proposes assistance on the right and you click to get them?
Yes, yes, you can do this. Let's try. Perhaps I have an example here. It's the same in Visual Studio Code, and I have the example here. If you don't mind, I show this in Visual Studio. Okay. but it works in the web interface too. So here I share something else. No, it does not share. 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 Random to live. Share. Share. Simple to share. I can stop share. I try stop share. Now share. Okay. I make some room here. Some room down. So I wanted to show the trigger map. Yes, yes, I zoom in. For example, do you see something? Okay. So I put the cursor in front of the question mark here, and I select the goal. Here. Selecting the goal makes a button appear. So I selected the goal, so it creates the introduction. Here we have let n be an integer. So it could be in words. Okay. And then we have to prove. So I can select here the new goal. And again, it can generate the code, but in fact, I don't want to do it that way. I want to use the contrapositive. So I will state that n is not even implies square n is not even. And as it will not do this alone, I have to provide a subproof here. And then from this, it is free to have the final assumption, which is n squared is even implies n is even. And here I can use the widget to create intermediate statement, for example. And so here I write that considering that n is not even, n is odd. So I say by the name theorem. So this theorem has been written before, and I omit this, but I'm not doing it because it will manage to find the proof, but it will be very slow. So it will need, for example, 2 or 3 seconds because it will search through the library, and we have to do some work to limit the search space so that it's not slow. But I could remove that, and so considering that n is odd, there exists same as before. There exists an integer such that. So I could use the simple quantifiers, but I do it on purpose to show that I can use the textual version. And now I compute the square of n, which will be a plus 1 squared, and this equals to 2k squared plus 2k plus 1, something like that, perhaps, I hope. And there exists an integer n such that n squared, no, I guess 2k plus 1, for example. So n is n squared is odd, and then finally n squared is not even, and the same thing, I precise the name of the lemma to save something. So mistake, I don't know, and this should be moved, but okay, I may have made a mistake. So when there is a mistake, it is very slow because he really tries to prove. But if he cannot, there is no parallel mutation that tries to prove the contrary or something, or counter examples. So for the moment, and there are some bugs which make that at times we have to reload. Perhaps it's the case.
It's reloading.
Yes, yes, perhaps
but
I have to.
nevertheless, the structure of the proofs is very clear. It's very nice. So I have quite a serious experience, I can say, with numbers. I told you about, and the two are complementing each other, as I see here. So the plus here is that it's a type system. There is a lambda abstraction. The one that I have great experience is the open proof for the natural deduction. There, it's the plus. There is something else. The graphical
Two,
tool
okay.
is plus, and but then don't see so clearly the structure of the proof. So you see everything is nested, and the lambda abstraction is available. So the students will learn the structure, the function, the partial function. So there are quite many concepts that will be learned.
Okay.
I can see it very clearly. But nevertheless, the two are complementing.
Yes,
There's no
yes,
competition.
of course.
There's no competition, but there is a complement. It will be nice. I believe if I have to teach logic, I'll choose both.
Yes, in fact, this tool is not good if you want to teach propositional logic or even first order logic, because it used some tautology tactics so that the logic statements are put in one line. So that is not really good, except if we made a special lead that is robust to tactics, but if not, so I want to show something else, but I don't know if I have the focus here. The last thing, but I will not do something, just show time.
I will consider this as a second. The other one is the baby course, and this one is the second.
Yeah. Okay. Yes.
Second level
second
learning.
Second level of learning. Okay, but in a high school there is no first level logic.
Oh,
there is
actually.
no logic course, not in France.
Computer student out.
And I would like to show that some other subjects, for example, in 12th grade, can be. So let's share this. Share. Sharing. Stop. Share. And now, just this. You have here a proof of the squeeze theorem, which is that if a sequence is between two sequences converges toward the same limit, then the sequence in the middle converges to the same limit. So that shows that the same software can be used to teach, for example, basic analysis, basic calculus. And we show here too that the fact that, for example, U, V, and W are sequences, are functions from N to R, is expressed by a membership statement and not by a typed judgment. So you have U belongs to R to the N, so it belongs to a set of functions and not is typed N towards R. So
here the example. So there's quite nice already two quantifiers exist and two such that for every M.
yes.
So here
Yes.
they learn the quantifiers explicitly by simple.
Yes, we could use this in, for example, first year undergraduates, for example, with the quantifier version.
And the negation, I guess that here they will learn the negated formulas of nested quantifiers, because that's a good concept, a living concept for logic students. To pass the negation, to have several quantifiers preceded by a negation, and to pass the negation inside of the structure of the quantifiers and of the logical operators also. Are there questions? Welcome.
Yeah, actually, I very much like this, especially the discussion about the number types and the partial functions.
Okay.
Very important thing connecting normal mathematics to these underlying systems. But then, and this actually has to do a bit with the discussion that you already started. I think the risk here is that you don't really learn what a proof is. What you learn is some tricks that you can use so that you make Lean satisfied, but you don't really know what a proof is. You learn to do some proofs, but you don't.
From the student point of
of a proof.
you mean?
Yes.
Yes.
And I would say that at least my experience from teaching and learning is that the best way to learn what a proof is actually to show the rules of natural deduction for logic, and then say, because this defines what a proof is, and there is nothing else than this, and then you know that when you add rules, which is what Lean does behind the scenes, then you extend the definition of a proof, but you are at all times certain about that what you are doing is a proof and not just them.
Yeah, I understand. In fact, I would have a short and a long answer. The short answer is natural deduction is not in the curriculum at high school. And the long answer would be during all the learning process since babies to adults, the students first learn the process and then learn to abstract it. For example, the notion of functions. The young secondary school students learn them as a process. You take a number and you put it to the square and then you add one. And this is very progressive, that they access to a function as a mathematical object that you can derive. And when they arrive to university, they have that idea that function object, but they do not imagine that the derivation is itself an object. So this process is quite long, and I think that at a high school level, it is too early to imagine proof as an object, in fact. So I think that discovering it through the process of proving is the natural evolution of the mind.
No, I don't think you need to go as far. If you teach natural deduction, you say that these are the rules and you have to obey these rules. Then whatever doesn't follow from these rules is not a proof. That's what
I understand.
So that there's never an uncertainty. But I know that this is not most countries don't have this as a high school in the high school curriculum. That's a pity.
Not even in math, right? What I learned in math, a proof is a sequence of statements. All of them are kind of obvious and build on each other. We were never told that a proof is some funny natural deduction thing. So I think we have to be careful what is supposed to be taught. This notion of natural deduction, I think, is not supposed to be taught. Even if you like it, and I like it, but
better teach the natural deduction. How?
The question of whether you want to conform to the current curricula and then it means you do not want to teach it, or if you want to be more radical and say, no, this is the better way to learn mathematics.
In fact, we could be radical, but our process is to try to convince teachers. And most of the math teachers in secondary education is not sensible to logics, in fact. And we saw in the survey most experiments done with proof assistants for teaching were done by people that are in the proof assistant community, that do proof assistant in their research, and naturally they try this with their students. But the opposite situation, to go towards teachers and convince them go to proof assistants is as far as I know, very rare.
And I think the idea of using a proof assistant in the first place is already quite radical.
So if they learn proofs in this way, so proof is whatever Lean accepts. So if you test it later by asking them to do proofs without using any software.
You mean it is as an aid?
Yeah, I mean, do they also learn to do proofs independently of using a software?
Yes, I think it is not enough. It is not sufficient. It is complementary.
Yes.
I think that people working on waterproof actually did that experiment also. So they did. Yeah, so, well, I mean, it did actually work better than so it was not as good as if they had the tool, but they could still, like, they had learned something about how to write a proof even without using proof assistance. I think it was like somewhat positive.
Because even those courses,
And that was with university students and not with high school students.
there are already automated courses in analysis. First course in analysis with integrations and set theory and upper level analysis. So there is already over there quite a lot of software that is somehow independent of us, as if they're going back to the old days of French calculus people who said we don't need logic or something like that. But it is needed logic. So.
Yeah.
So there are different proof systems. So you have the Hilbert style proof system, natural deduction, sequence calculus. And whenever you start with the Hilbert style proof system, then for classical logic, you can then show that the deduction theorem holds, so that you can then open boxes and contexts like what you do here. Why have you chosen to go for the natural deduction and not for the Hilbert style? Because the Hilbert style, I just heard it, it's a Hilbert style proof is a sequence of formulas where each formula either is an axiom or follows from previous formulas. That is the most exponent rules. That's it. So it's the simplest, most elementary proof format that exists, and the rest is basically making it more, fancy. So I was wondering why did you make that decision?
I don't know what would you imagine would be the difference in practice between your proposition, Hilbert style, and natural deduction, because we did not really consciously chose natural deduction over something else, in fact. So what in your proposition, what do you imagine would be different in the student activity?
So the Hilbert style proof system is the simplest proof system you could imagine. It
Also the most ugly.
It requires a bit of work. It is maybe not as natural, for instance, whenever you want to work with lots of implications, but it is, for instance, for equational proofs.
Perhaps I imagine, in fact, for example, in the geometry, in the US education, you have that sort of two-column proofs. In the left column, you have the statements, and in the right column, you have proofs, statement, or a sentence to explain. And what happens is that you have no possibility of case dissolution. You have no possibility of subproofs, and the data are introduced at the very beginning of the exercise, and there is no need to subprove for all something, quantify in fact. What is different here is that you have the possibility to subproof, and so the expressivity is mainly the same as in the underlying system. You have the same expressivity. So you can do, if you want, you can do all proof at university, for example. I don't know if I answer.
So my question is it really necessary to introduce natural deduction at the high school level? Because then what you mentioned is the proof structure itself becomes more clear, while the proofs you want to do, for instance, in analysis, can also be done in a Hilbert style proof system. So my question is really, why do you think it's necessary to introduce natural deduction already at high school?
It was me who said so. So
if
you don't agree, so then you don't need to. But I think my point was that it's the reason is to make people understand what a proof is, rather than just understand to do certain steps that are.
But then
Can I maybe
is simpler than the natural deduction.
There's a duality, like the notion of proof is simpler, and then the proofs themselves are complicated. So there's an approach in which the proofs are simpler and the notion is more complicated, but they're not reflecting on the notion, they're doing proofs.
Yeah.
Can I maybe add about, because we had a discussion yesterday, but I don't think that many of the people were here, about natural deduction rules. We actually have a course that is in the 4th year of Faculty of Mathematics, but we started a course on introduction to interactive theorem proving using Isabel. We actually use just natural deduction rules for the first 2 weeks. And the interesting thing is that those are students that are on the 4th year, but this is the program that has minimal mathematical logic courses up to that point. So those are students who it's not like they are not on the high school level, but their knowledge of mathematics and mathematical logic is almost like the high school level. So our experience with natural deduction rules is that students actually responded very well to those rules. We used just Isabel apply scripts, so nothing fancy, not easy language, nothing you didn't have any how can I say visual addition. So students were really quick with learning and adjusting to that type of proofs. Since you have simple proofs, you can start with simple theorems. You can use very small examples and introduce rules basically one by one, and you can make combinations that students can easily comprehend. And since you're using a computer and students are typing all the time, they get a lot of dopamine from quickly getting to the place where they are successful in a lot of small solutions, and they are really happy. And we get them to stay through the 3 hours course of lectures without even going outside for the breaks. They're supposed to have two times of 15-minute breaks. Nobody uses them. They are there for the 3 hours from the first class up to the whole semester. And we start with just natural reduction books for the first 2 weeks.
It's really addictive.
That is our experience.
Be careful in the design of our proof system that we do not make them too addictive.
I think the discussion about what particular proof system you take is actually misguided or misses the point. I think what we're seeing here is that you're actually trying to go towards informal or things that look like informal or declarative proofs. All of your tricks that you've introduced, both tricks and structures, try to do that because that's what students are supposed to learn at that time. It's very much in keeping with other things, other styles of teaching in schools, like you teach gymnastics by oh, look how I do this, and then somebody is somewhere on that thing, and nobody really tells you the torques are like this, and the center of gravity is like this, and the motion vector is like that, and I can prove that you can do this. So we don't teach like that, right? We basically teach by, oh, watch me doing it. And that's what you're trying to do here. And in that, it's hiding what's actually going on, just like in gymnastics, where we're in the gym. You don't have a blackboard there, which would kind of tell you what is a proof or what is physics. And so I think this is very well done, and it really doesn't matter what the underlying proof system is if you're doing your best to hide it anyway.
In the didactic literature, I think that they pointed out that learning a proof by solely imitation is not enough, and that it would be a plus to teach some logics finally. And here we're a little in between, because as you said, we try to go to the practical things done in class, but on the other way, by selecting, for example, the vocabulary, we tend to try to clarify that there are different proof structures and identify them. So I think it's like in between to have a support to talk about logic, but without breaking the habits too much.
How long are these courses? High school for 12 grades. How long is the course?
How long is the course? As I said, in 4 times an hour and a half, some 10th graders completed the progression. I mean, one third or 1/4 of the students, and many of them completed half in like 6 hours.
What are the interests of those students? Are they inclined toward computer science and mathematics?
Yes, it was a very particular situation because it was interns at the Computer Science Institute. It was a 1-week internship, and they chose to go to a research institute in computer science. They were particularly probably interested in those things.
What is your intuition? What is the percentage of the teachers existing in reality at high schools who can deal with this setup and understand what they're teaching?
Really, I don't know, but we talked with some, I don't know how to call this, some trainers of teachers, and they said, "Oh, more than doing this with high school students, you should try it with high school teachers."
Yeah, I'm quite skeptical. Quite skeptical there as well, unfortunately.
Yes.
What about computational linguists? Do they?
They don't exist. That's a set of size 0.
Do they choose to learn such concept?
Sorry?
You didn't pay attention. Are there some students who are interested in computational linguistics and take such courses? Or because lambda abstraction is an important tool for computational linguistics. You didn't pay attention to that. Probably next time when you teach such course, try to see whether you get students that want computational linguistics.
I don't know.
Well, there is
Sorry,
a
that was
famous lambada,
perhaps,
the lambada.
So you have the instances you've shown of assistants where you can like based on sub goals, whatever, insert things automatically. It looks like in a lot of the proofs, a lot of the longer, more complicated statements are the sort of things that are like pasting in definition, like in line 18 or 20. Like, have you given any thought to whether the student could instead say, like, U converges to epsilon, colon, and then the definition is imported, right? Because it's, I mean, it's true since that, but it's essentially just restating it, right? And so if the student instead wanted to say, okay, I want to use this hypothesis, you look up what the definition is.
You mean to search the premises, to search the definitions, to see what is used?
Or essentially a way of saying, I want to use the fact that certain thing is true, right? Like we know U converges epsilon or L, whatever, to L. So please insert the definition with those. In many of the example proofs, it seemed like that was a lot of the kind of boilerplate. It's like clearly the student is saying we want to use this now, but it's not exactly the subgoal. It's saying like please give me the overwhelmingly most salient fact that's relevant with the thing I thought.
Yes, for the moment there is no existing features to make the adequate definition appear or to search into the definition, and even the unfolding of definition is here is implicit. You don't have to explicitly ask for folding, but just state the fact. For example, you have an assumption that you converge to L,
and if you directly state, as done here, the definition, and it's accepted, but you don't have some didactic help to search the definition. You have that in there is another software that I talked about this, named the adduction. It's based on Lean 3, in fact, and you have an interface and the list of available definitions, and you can ask to unfold that definition by clicking. But this could be since there is access to program widgets, and that programming this you have access to the proof structure, etc. It could be possible to create these sort of things.
About that, I want to make clear that it's not that bad anyway, because we do want on paper that the students should be made clear by themselves in a full line their definition, but it's something that often they do not. So we should not maybe entice them to not do it, and clear for them that they should do it.
Now, from our point of view, it could be interesting to have this parametrizable, so that the teacher in the end could choose if that sort of aid are available or not. For example, here with what I showed directly proposes to introduce the right connector, but this could be deactivated, or there could be a choice of connectors to introduce without directly pointing the right one. So it would be better if we could tune depending on the teacher, depending on the level, depending on the month in the year. If
so, something specifically. So, as you pointed out, and with automatization, sometimes you need to compete because it's going to be slow. But more generally than that, I think that, for example, something that I face with, and I think is true with the ISAR or things similar, is that you might end up just trying to be the shortest to have the system automatize the proof for you. And so I think that's something difficult, but how do you think you could control that? Because if it's bad that they don't have to state the theorem that they want to use. But,
yes, you're right. You're right. These should be options, in fact. But in fact, I thought that in this project, the first step is are we able to guarantee that each trigger step is accepted, and the second step is how once the system knows if it's true or not, how can it produce a feedback to say, okay, I know that it's true, but you should justify it more. And I think that is a complementary problem. So it's in future work.
Some more questions? Okay. So my turn to chair this afternoon session, or maybe will be. Okay, well, you're the first after.
Sometimes